In this video, we're going to go ahead and integrate arc sine x using differentiation. First, we present the derivatives of inverses of the main trigonometric functions. So let's start with sine inverse. The derivative of sine inverse of x, let y equal to sine inverse of x, hence sine y equal to x. Now we will use this triangle which has an angle that's equal to y, and the sine of this angle is the opposite divided by the hypo equal to x. So now that we have sine y equal to x, let's do the derivative of both sides with respect to x. So derivative of sine y with respect to x is equal to cosine y dy by dx. And derivative of x with respect to x, d by dx, will give us 1. Now all of this imply that derivative dy by dx equal to 1 over cosine of y, and we can get cosine of y from the triangle, which is going to be equal to square root of 1 minus x, but since cosine y is in the denominator, so it will be 1 divided by cosine y. This is equivalent to cosine y from the triangle. Now let's go ahead and get the derivative of cosine inverse of x. Also, we will let y equal to cosine inverse of x, hence cosine y equal to x. We're going to have to provide another triangle, and this triangle has the angle y, and cosine the angle y is the adjacent divided by the hypo. So we're representing this equation also using this triangle. Now we will get the derivative of both sides of this. So derivative with respect to x of cosine y equal to negative sine y multiplied by dy by dx, and then derivative of the right hand side is dx divided by dx equal to 1. All of this implies dy by dx equal to negative 1 divided by sine of y. Using the triangle, we know that sine of y is equal to square root of 1 minus x, but sine y is in denominator, so we'll put it in the denominator. So this is the derivative of cosine inverse of x equal to negative 1 divided by square root of 1 minus x. Just like this is the derivative of sine inverse of x, 1 divided by square root of 1 minus x squared. And as expected, the only difference between these values is just the negative value for the cosine as opposed to the sine. And that's expected. Now let's take a look at the derivative of tan inverse of x. So we'll go through the same procedure. Let y equal to tan inverse of x, hence tan y equal to x. We'll get another triangle, and in this situation, the tangent or tan of y equal to x, because tan of y equal to the opposite divided by the adjacent equal to y. So we will proceed by derivative of both sides. Now derivative of tan y with respect to y equal to sec square of y dy by dx, and derivative of x is going to give us 1. So both of these will imply dy by dx equal to 1 over sec square of y, but we know that sec of y is square root of 1 plus x square. So since we want sec square, we will get the square of the square root of 1 plus x squared, which is 1 plus x squared. Also in the denominator, because sec of x is the denominator element. Now that we have done all of this, we will now proceed to what we want, which is performing the integration of each and every one of these functions without doing integration. Hypothesis. For f of x equals to arc sine x or arc cosine x, the following integration by differentiation is valid. What we mean by integration, we're going to do integration, but we're not going to do any integration. What does that mean? That means we're going to perform integration using differentiation. So the integral of f of x dx, we're going to do it using differentiation. And this is our formula. Integration of f of x dx equals to x multiplied by f of x plus 1 divided by f prime of x, where f prime of x is the derivative of f of x. Based on this hypothesis, the integral of sine inverse of x, that means we're taking f of x as sine inverse of x, will be equal to x sine inverse of x plus square root of 1 minus x squared, where you can map them 1 to 1. The x maps with this x, f of x is sine inverse of x, and 1 divided by f prime of x is actually square root of 1 minus x. Now that we have done this, let's go ahead and try to prove that indeed the integration of sine inverse of x dx will give us this value, which is x sine inverse of x plus square root of 1 minus x squared. Let's prove that. To prove it, we will just go ahead and integrate sine inverse of x dx. But then that's not going to be easy, so what we will do is we will use integration by parts. And to do that, we're going to have to multiply sine inverse of x by 1. So we have 1 dot sine inverse of x. And since that is the case, then we're going to have to choose one of them as du and the other one as v. So we're going to use du equal to 1. So since du equal to 1, then u will be equal to x. And we have no choice but to use v for sine inverse of x. So if v is equal to sine inverse of x, then dv will be equal to du divided by the square root of 1 minus x squared. Now we just have to do the plugging. The formula, general formula, is integration of v du equal to uv minus integration of u dv. We're just plugging. So we'll just plug. V is our sine inverse of x. Du is equal to 1. And then integration of this value will be equal to x, which is u multiplied by sine inverse of x, which is v, and then minus the integral of u, which is x, and dv, which is 1 over square root of 1 minus x squared dx, which is right here. One more time. This is the formula, and we have the value for v, which is sine inverse of x, and du, it is equal to 1. That's why we have integration of sine inverse of x dx, of course multiplied by 1, but we just ignore that. That's equal to u dot v. Our u is x, our v is sine inverse of x, minus integration of u, which is equal to x, dv, which is equal to 1 divided by square root of 1 minus x squared. Now we have to find the value of the last term. Okay. So we'll go ahead and follow the last term. Let w equal to 1 minus x squared. Hence dw equal to negative 2x dx, and dx will be equal to dw divided by negative 2x. Therefore, integration of x multiplied by 1 divided by square root of 1 minus x squared dx is going to be equal to, we leave the x as it is, and we replace 1 minus x squared by w, which is going to give us x multiplied by 1 divided by square root of w. And dx, we found it to be equal to dw divided by negative 2x. So it's right here, dw divided by negative 2x. If we take negative 2 outside, then we will have negative half integration of 1 divided by square root of w. dw. And if we do the math, this integration is going to give us negative square root of w, which is equal to negative square root of 1 minus x squared. Since this integral is subtracted from the first term and the result of the integral is negative, and we have subtraction, so these two cancel each other, and the result will be integration of sine inverse x dx will be equal to x sine inverse of x plus square root of 1 minus x squared, which equals to x, and then sine inverse of x is our f of x, plus, and this is 1 over f prime of x. Thanks to our hypothesis, it made life easy. Integration of cosine inverse of x by differentiation. Suppose f of x equal to cosine inverse of x. Based on the hypothesis, integration of cosine inverse of x dx equals to x cosine inverse of x minus square root of 1 minus x squared. Let's prove this. Proof. Integration of cosine inverse of x dx equals to integration of 1 multiplied by cosine of x dx. Now we can choose for 1 du. So if du is equal to 1, then u will be equal to x, and we have no choice but to choose v for cosine inverse of x. So if v is equal to cosine inverse of x, then dv will be equal to negative dx divided by square root of 1 minus x squared. Now let's get the formula for integration by parts. So integration of v du is equal to u multiplied by v minus integration of u dv. And this implies, if we just plug in, our u is cosine inverse of x, our du is 1. So we're doing integration of cosine inverse of x dx, which is what we wanted, which is integration of this, equals to, and then we're going to go ahead and plug in u dot v. Our u is equal to x, and our v is equal to cosine inverse of x, minus, we have to plug in integration of u, which is equal to x, and dv, which is equal to negative 1 over square root of 1 minus x squared dx. So we have to figure out this integration, and it looks like we have to use integration by substitution. So let's go ahead and let w equal to 1 minus x squared. Hence dw is equal to negative 2x dx. And solving for dx, we get dw divided by negative 2x. Now we will just go ahead and figure out the integration of x multiplied by negative 1 divided by square root of 1 minus x squared dx. We're going to plug in, instead of 1 minus square root of x, we're going to replace it by w, which is right here. And then we're going to replace dx by its equivalent, which is dw divided by negative 2x. The rest is the same. So we can see that the x will cancel the x, and we have negative 1 divided by negative 2. So negative goes with the negative. We have half. Let's take it outside. So it will be half. And then we will be left with integration of dw divided by square root of w. So we have 1 over square root of w. We have to do the integration with respect to dw. And that integration will be equal to square root of w, and that's going to be equal to square root of 1 minus x squared. Now we found this integral to be equal to square root of 1 minus x squared. So we have to replace this integral by square root of 1 minus x squared. So it then follows that integration of cosine inverse of x dx equals to x cosine inverse of x minus square root of 1 minus x square, which is equal to our hypothesis, because x and our f of x is cosine inverse of x, and square root of 1 minus x squared is nothing but 1 divided by the derivative of cosine inverse of x, thanks to the hypothesis. Next, we look at the integration by differentiation of f of x equal to r tan x, and this is given by integration of f of x dx equal to x multiplied by f of x minus half of ln the absolute value of f prime of x, where f prime of x is the derivative of f of x. Suppose f of x equal to tan inverse of x. Based on the hypothesis, integration of tan inverse of x dx equal to x tan inverse of x minus half ln of the absolute value of 1 plus x squared. The absolute value is not necessary because the value is positive anyway. Now, let's prove it. Proof. Integration of tan inverse of x dx equal to integration of 1 multiplied by tan inverse of x dx. Now we will use integration by parts. So we'll use du for 1. So if du is equal to 1, then u will be equal to x. The only choice for tan inverse of x is v. So v will be equal to tan inverse of x. That means dv is equal to dx divided by 1 plus x squared. Now we will go ahead and use the formula. The formula integration of v du is equal to u multiplied by v minus integration of u dv. And this implies integration of tan inverse of x dx equals to u multiplied by v minus integration of u dv with respect to x. So now what we have to do is we have to evaluate this integration. And to do so, we will let w equal to 1 plus x squared. Hence, dw is equal to 2x dx. And solving for dx, we will get dx equal to dw divided by 2x. Now we could just go ahead and plug it. So integration of x multiplied by 1 divided by 1 plus x squared dx is equal to integration of x multiplied by 1 divided by w instead of 1 plus x squared, because we said w is equal to 1 plus x squared. So we have x multiplied by 1 divided by x squared, and instead of dx we replace it by dw divided by 2x. So we have dw divided by 2x. Now the x will cancel the x. We have 1/2, we'll take it outside, and then we'll be left with integration of 1 divided by w dw. And this is going to be equal to half of ln of 1 plus x squared. Now that we have this, it then follows that integration of tan inverse of x dx equal to x tan inverse of x minus half of ln of 1 plus x squared, thanks to our hypothesis. And that's the end for this video, and thank you for watching. And if you like what we're doing, please subscribe for the channel. You have a great day. Bye.